Hello, everyone. Welcome to the Audio Precision webinar. Today, we'll be discussing Automotive A2B audio test with Mike Martin, and he will be leading the conversation and providing demonstrations in APX 500 software. My name is Paige Morford, and as the producer of the event, I would like to go over a couple housekeeping items before we get underway. So please note that this webinar is being recorded. Secondly, we welcome questions during the webinar. So if you have a question for Mike, you can submit it via the chat function in Microsoft Teams. So on your screen, you should see a chat icon in the upper right-hand corner to type in your question, or you may automatically have the window open. And throughout the webinar, we will periodically pause to answer your questions. And also, if you prefer, we will also be doing a live Q&A at the end of the webinar as well. Today, Mike has a lot of info to share with you. So without further ado, Mike, I turn it over to you and the floor is yours.
Okay, thanks, Paige. And I think we've got it set up here.
Yes, you're
so good day, folks. Thanks for joining. Again, my name is Mike Martin, and I think we've got a reasonably good schedule here for covering some of the key points of the Automotive Audio Bus, A2B. We'll go through our agenda here momentarily. Looks like this. We'll talk a little bit about the physical bus in operation. I'm not going to spend a lot of time, introducing the what is A2B so much. I think that information is readily available, but I'll talk a little bit more detailed conversation about the bus itself and how the data moves. We will talk about the Mentor A2B analyzer, which I'll be using later in this session, talking about the test connections that I make to the device, and moving then into the software end of things, talking about the Mentor UI for the analyzer, and then finally moving into some live measurements and finishing up with reviewing questions. So with that, let's go ahead and get started. Again, my name is Mike Martin. I'm the Marketing Product Manager at Audio Precision. I have a BSEE background with roughly three decades worth of experience in test and measurement. And today we'll be working specifically with a set of equipment shown here. I have an APX 555B audio analyzer. This is what I happen to have. It's not a requirement to make these tests. In fact, any one of our audio analyzers could be used with this kind of equipment. You see over to the far right the Mentor Automotive A2B analyzer, which is the device I'm using to talk to the slave nodes in the net, and so we'll be working with that directly. And because A2B devices are a little hard to come by in the open market, I'm using an analog devices evaluation board for the DUT, as you can see right here. This little board has the A2B interface, power supply input, and an analog in and out. And so we'll be exercising some of these things as we move along. All right. So here's a view in the upper right corner of a typical system. We've got an A2B master that is providing clock and synchronization, framing, low current power supply, and the connection is through a bidirectional bus, and it connects to one or more slaves. Here we see a microphone slave, and you can have many of these chained together. The maximum distance between devices can be up to 10 meters and the total network length up to 40 meters. The individual slaves can have a variety of functionality. So I'm showing here several mic devices, and here's a independent device doing ECU, and then we've got a couple of connections to speakers. But in fact, you could have in and output audio in and out on any one of these nodes, and that would be perfectly fine. So there's a huge flexibility in the topology of a potential network, and the master has to be aware of what's out there, and then once it has that information, it can communicate throughout the chain and maintain time-aligned representation of the audio traffic. We see here in the lower part of this picture that we have two kinds of cables shown. This one is the cable I'm using to connect from my master, which is that Mentor A2B analyzer. It uses an auto link connector that you see here, which has, in fact, it uses the old USB Mini V connector. And on the other end, it has a DuraClick connector. And so this is one typical kind of cable you might run into, and this is simply just another cable with DuraClick connectors on each end. You can see it's this basic twisted pair wire cable. It's quite simple, quite lightweight, and low cost, which is why the auto industry is especially interested in it. Okay, so again, it carries clocking information across the bus, control signals. So for example, if these slave nodes need configuration before they start up normal operation, that kind of control can be set up through the master into each one of the nodes, the slave nodes. The content data, once it's up and running, of course, is going both directions. And there is the ability to provide low current power, which is especially apropos for microphone modules. They don't require a lot of power to power those. Other devices, such as something that's going to drive a speaker, is likely going to have its own local power supply. So that's the basic topology that we're likely to see.
Hey, Mike.
It's interesting. Yeah.
I do have a quick question.
Okay.
Does the APX 525 support A2B testing?
Yes, absolutely. Yeah. Anything from the APX 515 all the way up. And in fact, I'll talk a little bit more about it further on, but we have something called APX Flex, which is the ability to run the APX 500 software without actually using one of our analyzers. And there are some use cases where that might even be an appropriate solution for A2B. So, so yes, absolutely, any one of our hardware analyzers is useful with this test. Okay, so one of the things that I noticed back when I started staring at A2B initially was it was really hard to get detailed information about exactly what was going on in the bus. I think that as the auto manufacturers move into consideration of A2B for implementing in one of their vehicles, the data is made readily available, but for the normal rest of the world, it seems a little hard to come by. And one of the documents I did dig up, I went looking for the original patent that Martin Kessler at ADI received, and of course that's all public information. So down in the lower right corner here, you can see the patent number. It's about a 50-page document or so. It has a lot of images in it, and one of them is this picture that I'm showing you here. So if you like to have that level of knowledge, I encourage you to dig up the patent and have a look at it. So I've done a lot of work in my past with high-speed serial data buses. I was deeply involved in the early days of serial ATA, SATA, and USB, and a number of other standards, HDMI, as they developed, doing testing of the physical layer. And so for me, it's kind of a natural place to start of, what's the data being transmitted look like, and how does it move? So this picture, I think, is useful because it demonstrates that there's a super frame structure, and the length of that is generally described as 1024 bits, and I think in most or all of the implementations out there today, that's what it is. It seems from looking at the patent that there's a lot of wiggle room in how this could actually be implemented as long as the general structure is followed. And the idea is pretty basic, because what you're doing is setting up an architecture that allows a specific amount of data to be transmitted reliably in a specific amount of time, and in doing that, you get the ability to maintain the real-time relationship between the channels that are being moved around. So again, 1024 bits is the length of the super frame, and that frame contains both the downstream transmission data and the upstream transmission data. So as the data is being transmitted, there's a control frame, it's about 64 bits, and then you have one or more slots, up to 32 slots total across this, and a slot can have a single channel or multiple channels, and you can have a total of 32 channels represented here. Note that's not 32 channels downstream and 32 channels upstream, that's 32 channels combined. So each channel is allowed a 32-bit sample, and if you don't require 32 bits, it's just padded with zeros. We'll see that a little bit later here today. So this is basically what the data looks like as it's moving across. I've noted as I've looked at things, especially in the patent, that some of the information doesn't quite gel exactly, but I think it's good enough to get the idea. For example, if it basically says there are 32 channels available and 32-bit data, and when you multiply those, that comes up to 1024 bits. That doesn't really talk about the fact that there are these other 128 bits used for the synchronization frame. So I think there's, when you get right out to the end, if you're pushing the very maximum possible, there's probably some limitation that comes up a little sooner because of the fact that we're consuming 128 bits here. But the super frame period is 20.83 microseconds. The data rate on the bus is generally described as 50 megabits per second. It's the patent shows it as 49.152 megabits per second. It doesn't really matter as long as it's held to a rate that allows these 1024 bits to be moved in a specific amount of time. Okay, so there's a little bit about the bus itself. When the bus turns on, it goes through several modes. It goes through a discovery mode that allows the master to verify what nodes are out there. And it goes on then to a second mode, which allows I2C data to be transmitted to the nodes for node setup. So if a device needs to be programmed, if a slave node needs, for example, filter coefficient data put into it, that can all happen from the master during the startup process during this second mode. And finally, it moves into normal operation where the data being transmitted and received is all I2S data that is being passed through using a time domain multiplexing technique. So,
Mike,
yes.
before you move on, I do have 2 questions for you.
Okay.
The first question, are there any specific license requirements as in version 6 or version 5?
I am not aware of any, but I haven't, I personally haven't gotten to the full point of, trying to deploy something. So I don't know if exactly what constraints there might be out there. Having said that, I also haven't seen any references to that along the way. So frankly, I'll have to say I'm not certain.
I'll chime in, Mike. Actually,
yeah, go ahead.
This is Eric for the audience. So no, version 5, version 6, even version 4.6 would support APX software. Will support the A2B testing. What you're going to just not have then at that point, if you don't have version 5, is you're going to be lacking the transfer function measurement capability that was added with version 5, and the multi-input capability that was introduced with version 6.
Thanks, Eric. I was confused. I was actually still thinking about licensing of A2B, not licensing of our software. So thanks for that.
Yeah, no worries. I'm pretty sure the question was in the context of which version of APX software. That's
yes. Thanks. I recognize that. Okay. So Eric, what Eric said is absolutely right. Okay.
So I have
in fact, I should, and we'll see this in the next slide. I'll make one point here that the way we communicate for testing with the master is through an ASIO interface, and so any of our versions that support ASIO can be used. Anything that was produced prior to our implementation of ASIO won't work. So I think the very oldest firmware sets for our analyzers don't show this, but as Eric said, the more recent ones do. So this diagram shows the system I have here set up today. I've got a PC that is running the Mentor software for controlling the master and the nodes. And I also have the APX 500 software, which is used to operate the analyzer. And both of these devices are interfaced into a single PC so that I can share data back and forth. All right.
Mike, I do have another question from the audience.
Yeah.
Is it possible to use an A2B analyzer also in slave mode to simulate speaker and mic nodes?
It's my understanding you can. There are quite a few modes of operation, and in fact, I'll even mention while we're here that Mentor has a second product that's their A2B monitor, which can be placed in line with slave nodes so that you can monitor data at a specific location. One of the things that's kind of important is that as data is received by the first slave, that slave has an opportunity to send its own data down to other slaves in the chain and vice versa, and that traffic may not be visible all the way up at the master level. So there may be cases where you need to have a tool that lets you see what's going on specifically between two slave nodes. And so there is a tool to do that. I didn't try to prepare for demonstrating that as well, but that tool is out there, and I expect that there are a lot of similarities with the UI once you're working with that piece of equipment. So thanks for the question. All right, So this is the equipment we'll be using today, and I think I've said what I need to about it. We'll go into more. One thing that's really important is that you need to make sure if you're going to use this equipment that you get current versions of software. Version 6 isn't absolutely required. Certainly, version 5 would work adequately to make these measurements, but today version 6 is our current firmware. And on the Mentor side, there are 3 pieces of firmware or software. There's a firmware set that is specific to the analyzer, and I'm aware that version 5.2.8 is the preferred version, the latest version. There is also a version of the Mentor ASIO interface, which is version 3.19, and that one's kind of critical. There were some issues in some of the older versions, and it's strongly recommended that you get the latest version, in fact, for all of this. Finally, there's a version for the user interface portion of the software as well. So these 3 modules are required to be installed on your computer that is connected to the analyzer, and the AP software is required to control the audio analyzer. All right, so I think that gives us a pretty good picture of the system that we'll be talking about. So next, what I'll do is give you a little deeper view of what's going on through the user interface of the Mentor system. And to do that, I'm going to actually shift over to the live UI, and I've kind of got this set up so I can look at the UI and our APX software simultaneously, but I'm going to stretch this out so it's a little easier to see. So the process is that you need to, when you're using this software, you need to describe the network that you're going to use. And so there's a workflow associated with this software that is kind of left to right across these buttons, tabs, if you will. And then once you select one of these as the step you're working on, there's a series of areas to address. Some require attention almost every time, and others, like peripheral configuration, may not even be relevant to what you're doing, and you won't have to stop and make adjustments. So, for example, you can see here that I've got the ability to create a brand new configuration. I can load a previous configuration, or I can save something that I've configured. And so I've got a configuration loaded in here right now that we'll use in a few minutes to look at the operation of 8 channels of digital data initially. And so here is an area called streams where you're basically defining the data type, if you will, from a programming parlance, talking about this as a 32-bit sample and how many channels there are. So you set up this initial information, and then you move across to define other elements. We need TDM data, so that's selected here as opposed to some of the other choices. We're not doing anything with the peripheral GPIO or anything like that, so we can basically leave this as the default for this. The board I'm using is a board eval AD2425WG1AZ. So it turns out that this WBZ/WGZ definition, which is loaded in through the predefined peripherals list, can can be used straight away to help you get through and get to a useful configuration for that device without having to go through and figure out what each one of these items is. Moving on, we've got nodes. So in this one, it shows that we have an A2B analyzer. It's showing an 802410 and an 802425 as the two slave nodes, with the analyzer being the master. And again, you'll notice there are multiple tabs in this area. So the configuration is again moving left to right. You start with this. It already knows that this is a 2425 analog devices chip and that it's a slave. So we move through, it's got inputs and outputs. And so we've specified those. And finally, we get to the networks area where we talk about the sample rate, the slot size, and a number of other things. Configuration registers, which again, if you're not using a lot of the general purpose I/O, you won't probably have to make too much attention with this. But moving on, representation again of the network, and here, you know, we had the opportunity to include the 802410, but that's sorry, yeah. So we've got that here in this. Here's a table that shows the connection between the analyzer inputs and outputs and the inputs and outputs of the slave module. And so if we had many slaves, this table would be more rows and columns. And finally, we have a slot view, and this one is kind of interesting to me because it gives you information about bus usage. So here we have total bits available, 1024, so that's our super frame size. And right now with the 8 channels that we've set up, we're using up 676 of those bits. So we've got a total bus utilization of about 66% at the moment for this particular configuration. All right, so once you have this configured, you move on, talk about node simulation. So here is ASIO as the source, and this board has the audio output that I talked about. So here I've got the ability to send ASIO data to the audio output, and likewise the audio input out to an ASIO channel. I'll use this later to show you slot activity. It's a kind of a handy feature. Again, some GPIO stuff that I'm not going to spend time with. And so once we have this configured, then we go through a process of that, starting the discovery mode, moving through the I2C GPIO configuration, and finally going into normal operation. So it's discovered successfully, the bus is now running, and I'm ready to start communicating with it. So before I run off to do a demo, what I think I'll do is come back over here to our slide set and move down a little bit to talk about the Audio Precision UI. And again, it'll be a little more interesting if we do that through the real software. So for those of you who maybe haven't used the APX 500 software extensively, I'm running in sequence mode. There's also a bench mode operation I'm not going to talk about today, but it's very cool if you have the use for it, the need for it. The sequence mode provides a sequence that can be run. So instead of having to write a program for automation, you can define a sequence and then run it over and over again simply by hitting the sequence run button that I'm sitting on right now. So I will open up some predefined projects in a minute for the demo, and we will run some tests. The center area allows us to set up individual tests or the underlying configuration of channels. So right now I'm in the signal path setup portion of this, and I can define the channels. So for example, here's the ASIO connection, and then once I specify ASIO, I need to tell it what kind of ASIO device I'm talking to. For example, I could be talking to a sound card, but today we want that A2B ASIO interface, and likewise down here. And as soon as I go to ASIO, I think it defaults to whatever the other one is set to. So notice that immediately I'm showing 8 channels of possible data here. So this is the signal path setup area. It's also used, as you could see, for any other channel selections. So it's perfectly reasonable to mix between analyzer channels, which might be unbalanced or balanced channels, and ASIO. That's part of the configuration. Once you have the channels selected and settings set up, you can move over to the measurement setup, and depending on what measurement you choose, you might have more or less things to adjust. So here's a setup for the frequency response that shows it at 20 to 20K span, sweep speed, channels that will be used, all of that. So that's a very quick overview of those two pieces. This, of course, is the results section, the output graphing and charts that come up. And down here in the lower left corner, we have some really useful monitors. One of them is an oscilloscope display, essentially an FFT, so we can get a frequency view. This can be popped out, which I'll probably use a little bit later. And so this allows us to make very good measurements on the data that comes back from the A2B bus. All right. So just to keep myself synchronized here. So what I'll do first is an 8-channel loopback. So on my board, I've added a cable that will loop the digital transmits to digital receives, and we'll be able to acquire that information and make measurements on it. So in fact, I've already loaded that. It was what I loaded when I was talking about this portion of it. I'm going to like to be able to see the slot activity, and I'll just shrink this back down so we can see both of them a little more easily. All right, so let's recall my project. And here's an 8-channel demo. No, I don't need to save what I was doing before. And I've already started this during that bit of work we did over here, so it's in running mode right now. And you'll notice that if I change over to the signal path setup, I can turn on the generator, and what you see is the channels are live. So I have transmit and receive slots that as soon as the signal appeared, they came up. I've told it to apply a -20 dB full scale signal, and you can see that that's exactly what the measurement is showing for our RMS level. So so this shows the system is working, that I'm receiving data on all 8 channels. So what I'll do now is just go ahead and run the sequence, and then maybe we'll experiment with a couple of the features of the system here as we move along. So this is now doing a THD plus N measurement. It will move to frequency response. You'll see a nearly perfectly flat frequency response briefly. Now signal to noise ratio, and finally interchannel phase. And our test has completed for the steps that I selected. And so we can look at some of these results here, and I think it tells a really strong story about the A2B bus. We have 24-bit data, and if we had an absolutely perfect system, we would have 144.5 dB full-scale range on that. The system here uses dithering, and so we don't quite make it to 144, but we're very, very close to it. So this is an exceptionally clean signal, and the signal-to-noise ratio tells the same kind of story. If I was to jump down to that measurement, you know, it's showing 142 dB across all these channels. As we saw briefly, the frequency response is very, very flat. You can see I'm have very small steps in my scaling, and yet there's no variation. That's what we expect out of digital response data. So this system is fully operational. The phase between channels is very good. I'll show that in maybe a couple different ways, but if I turn the generator back on, you can actually see this running. And down here, it's showing the scaling as phase in degrees with 0.00005 degrees plus and minus. And so again, basically, we're just seeing very, very minor variations in phase across these channels. So, and again, this is interchannel phase, just to be specific. So this shows some of the robustness of the underlying digital foundation that's moving this data back and forth. There's some interesting things that we can do. We have a number of signals available to us that are specific to digital that we can switch to. We've been using a sine wave up until now. This channel is one that's been made with a little utility that we produced. It's available free of charge, just download it off our website. This allows us to put unique signals on each of these 8 channels so that you can verify that that what you see is really more than just all these channels having identical content and not really being able to discriminate between channels. You can discriminate. I'm going to expand out this plot. And so what you see here is each channel has its own unique color. That's the index in the upper right corner. And we have 8 tones that are being put out, 1 tone for each channel, which is why they're all different colors that align with what you see in the index. And also a very slight frequency difference down here at a low frequency point. And again, you know, I think this shows off a lot of goodness about the system, that we can actually produce a response like this that is very carefully time aligned, repeatable, clean, very clean data. All right, so there's one interesting thing. We have some other capability relative to digital signals. We've got walking ones and walking zeros patterns, and for that it might be most convenient to look at a bit display. And so here, ones are walking across the bit pattern for the signal, and you can see as the one gets closer and closer to the most significant bit, the amplitude gets higher and higher. You'll also notice that when it resets back here, which is because this is a 32-bit slot, and we're only using 24 bits of it, so these 8 bits are just padded zeros, and that's what the system does. You know, for example, in those 1024 bits of the super frame, if you don't use all of the slots and completely fill it up, the rest of the space is still there. The timing is still held. It still transmit 1024 bits. It's just that it's either noise or zero data that is in the unused space. All right, so just a quick sanity check for time. I think we're doing all right. So we've got a number of things that you can do that are relevant to digital signals in particular. We've investigated a few of those. So at this point, I'll move on and just pop briefly back to make sure I stay on track with what I was going to talk about. And then we'll move on to the next thing. So this is the configuration we've looked at, and I've shown a 515 analyzer here, but it could have been anything else. And frankly, right now in this particular configuration, the analyzer isn't doing anything more than allowing the license to run for the APX 500 software. And in this configuration, I could have just as easily been using APX Flex, which provides the licensing through a USB stick. But this is a representative of what we just looked at, and the fact that we transmitted and received the data into a slave through the analyzer. So here's an example where you would engage the analyzer. We can have a measurement mic, and of course there'd likely be a power supply in here to power that, and it would go into one of the channels on the analyzer. And then, for example, we could test a loudspeaker that was being driven from the analog out of the board. We will do something similar to that, but before we get there, what I'll do is just start with a quick 2-channel loopback of the board. So I'll remove my digital loopback cable that I had and put in a 3.5 millimeter analog loopback from the output to the input. And I will go back to our system here. I will stop the A2B channel, and I'll load up a 2-channel analog loopback session that I have here. So these session files that you see the little A2B on for the icon are associated with the analyzer, and so I should be able to just start that, and there you see 2 channels active. It's still, I've got the generator on, and so it still sees that traffic. Okay, and I will also open a project that is specific to the loopback. All right, so we're familiar with the UI. I'm going to go ahead and run this test. And you can see that it's doing a set of things, THD plus N. It'll go into frequency response here. Signal to noise ratio. And I didn't populate this with too many tests, but we've got information. So it happened to stop with the signal to noise ratio, and you can see the measurements made, and it's nowhere near that 142 dB number that we were seeing before, but and it's expected to be less because now we're working through analog circuitry. So now let's look a little bit at what we saw here. The frequency response is still very flat. Of course, I don't have that same tight scaling that I had before, and if I zoomed in on this enough, eventually we would see some variation, but it is still quite good. So this is a nice, well-designed flat response for this little input and output, and I've got a few other outputs that I can look at there. I think I'll move down. We looked at signal to noise ratio. This isn't so impressive to me, except it gives us the foundation for saying, okay, we've got a reasonably good connection for analog. So now let's move on and do something a little more realistic. So I'll disconnect that loopback cable, and now what I'll do is connect up a powered speaker to the output. You'll hear a beep or two here. And I have a microphone, a measurement microphone, connected to a battery-powered power supply, and the output of that is a 3.5 millimeter cable that I can connect to the input. And so we can keep our two-channel control going here on the Mentor side, but I'll want to open up a new project. Oops, not a new one, an existing one. And here I'll do the speaker demo. So I am in my home office because we're all working from home these days, it seems like. And this is a far less than ideal environment for testing speakers, but I think we'll get enough of a feeling here for what it does and how it works. So I should be good to go on the measurement. I'm using a ground plane technique to make the measurement. And if our audio was good enough, you could have heard that chirp that I just did. And now we have the frequency response plot of this little relatively inexpensive powered speaker that I have here. Not bad. It's actually rated for 200 to 10K operation, and our results demonstrate that reasonably well. So here we've gotten to the point where we can do real work. We're making analog measurements and getting proper results on it. So likewise, if I had an audio or a microphone module here, I could have just as easily tested the microphones, and I could have tested multi-channel microphones easily because the infrastructure is in place to do it. I think we've demonstrated that pretty well here already. All right, so I think that's mostly what I had on my mind, and we are doing reasonably well for time here. I'll pop back to the slide set, and we'll just review. Here's what we just did. So we used that analog out to drive the powered speaker, and we collected the signal through a measurement microphone and made the analysis. All right, so at this point, I have one other little thing I'll at least present, but I'm not prepared to try to do a demonstration today. But are there any other questions as we get close to the end here?
So everyone, as a reminder, you can submit your questions via the chat function in the upper right-hand corner of your screen. And while we wait for questions, I will review a couple resources that are available to you. So if you go to our website, www.ap.com, we have a myriad of audio test assets available, from application notes to data sheets, and there are many free downloads you can access at no cost. And we also have the Audio Precision blog, which is also on ap.com. We regularly publish content that goes over measurements, best practices, as well as tips and tricks. So be sure to check that out. And of course, you can find us on various social media platforms, including LinkedIn, Twitter, Facebook, and Instagram, as well as our YouTube channel. And we have a variety of videos available for you to learn more about audio test. And if you have further questions, please don't hesitate to contact us. Our tech support team is a great resource and would be more than happy to assist you with your application. Mike, I do not have any questions that have come through the queue.
let's just look at one or two more slides. What I have here, direct my mouse a moment, is kind of, you know, one of the directions you could move if you were inclined. This shows a system that is based around A2B that includes a hand-free speech microphone array, and the tools exist today to make Polka measurements on such a link to actually verify and test the quality of speech that's received to the head unit in such an environment. So this system shows a KEMAR, head and torso simulator that's produced by Grass, our partner company. This has a calibrated speaker for the mouth, a mouth simulator, and we don't care so much about the calibrated ears at this point in time, but for this test, it's possible to reliably perform the same speech quality test over and over again to verify results based around changes that you might do to DSP or other elements in the system. So, like I said, we're not prepared to demonstrate this today. The tools are absolutely there and available to do it. Our APX Flex is available with Polka or the standard analyzer, and we have a number of psychoacoustic tests that are available. So this is something that maybe would be the topic for another webinar sometime down the road. If you have an interest in that, you can send the feedback to Paige. You know, I think we visited the idea of trying to include this and decided it was a little bit bigger task than we had time for in the hour. So here's an example of the output, and I don't know if I'll be able to successfully play the audio here across the track, but I'll try it. Paige, you can flag me if it actually doesn't come through on your end. I didn't get to verify this ahead of time.
Okay.
Seems like it's not going to play. So, in fact, I suspect it's in a conflict with my ASIO interface right now. So, at any rate, this is an example output from the APX 500 system that has made these measurements, and you can see that this result has some clipping that it has produced a much lower value for the measurement. And with that, I think we've mostly come to the end of our sequence here. Thought there was one more. Yeah, there are a couple more slides. Okay, so here's a plot of that data that we just saw the bar chart for, showing that the red channel has some clipping that is clearly identifiable, and that's degrading the quality of the speech. Again, another one, this one's relative to automatic noise cancellation and has the outside noise source was a motorcycle passing by the vehicle, and two different results for measurements in the system. So this is a representation of a test we're not doing today, but is doable. Again, if it is appropriate, it might become a topic for a future webinar. All right, so with that, I think we've come to the end of our time and our story. I'll mention to you that the Audio Precision website has several other A2B resources. You're welcome to go online and grab that. And I think we've come to the end. Thanks so much for attending.
Thank you, Mike. Well, I'll forward any questions that I get on after the close of the webinar, and we'll follow up with you all via email in the next couple days as well. So thank you so much for joining us today, and we hope this was useful to you.
Thanks, folks. Bye-bye.
Bye-bye.